All right, let's get started. I would like to welcome everybody here to the inaugural AI event for the AV8.AI community, and we're proud to sponsor this event with Algolux. So, AV8.AI is sort of a community service organization. I've spent many years in the industry working on AI and vision recognition development, business development, and ecosystem development for companies like Intel and Xilinx and some other startups, iCloud. And I felt it was time that we had a place where we could bring together an ecosystem of people that could directly connect with each other, support each other, find customers, find partners, find investors, to help them bring their video AI solutions to market. So that's what the genesis was for AV8, and I welcome you all to join. It's a free membership. There's no charge for anything. It allows you to connect online with people that are like-minded, that are trying to solve these video AI problems, like Dave and Algolux and some others that we'll be bringing forth. The Cadence will have a monthly event like this, and then we have weekly office hours, and then we have weekly in-depth interviews with people in the industry. So if you join the community, you'll have access to all that and all the people that are in the community. This is what the site looks like, some of the content. It's also we have an event listing for all of the video AI stuff that's going on around. I don't know if you know, there's a TinyML Summit going on as we speak, and then AI Weekly, and there's a whole listing of everything that's going on. There's a Computer Vision Summit later on this month, and another AI Summit by Matroid later on in February. So a lot of stuff going on. This is the agenda for this evening. Quick intros. Dave's going to talk, and then we'll have some Q&A at the end.
So my focus for the talk tonight is really around perception, computer vision, and really achieving much more robust results in challenging scenarios, which automotive is a great example of that. And I'll also touch a little bit on surveillance too. But I want to maybe make it a bit interactive and say, how many of the folks here are actually doing anything related to computer vision today? All right, actually quite a few. I'm assuming everyone is touching in some way AI and maybe deep learning in some fashion, either yourselves or your company. Is that fair? A good crew. And for the rest, ask questions, and we'll take it from there. So I'm Dave Tokic. I head up marketing and strategic partnerships at Algolux. Algolux, I'll give a little bit of an update on who we are, but we're a startup, or getting slightly beyond startup, we like to think, focused in this area of perception and applying interesting computational imaging and machine learning based approaches for those applications. So our focus really is around robust perception, and so we are targeting the safety critical type applications such as ADAS for driven automotive, or AVs, and surveillance as another example. I'll touch a little bit more about what we're doing. And we add scalability to that, and I'll touch on that in a minute. So application-wise, as I mentioned, primarily focused on automotive, ADAS and AV. We are working with companies in the AMR space, autonomous mobile robots. So you might see examples of the Amazon warehouse robot, or some other robots that move materials around warehouses or in shipping yards and things like that. So we are working in those application spaces, as well as also in the area of video security, which also has to deal with harsh conditions like low light and bad weather and things of that nature. In addition to robustness and scalability, and when we mean scalability, it means being able to support any camera, any application very quickly as compared to today's normal approaches. We are also doing some really innovative work in disrupting current technical approaches like maybe alternative sensing modalities rather than that give results like LiDAR, but maybe for $10. Or also just providing a much better approach to multi-sensor fusion for these applications. So while camera-based is very central to what we're doing and most of our customer engagements, we are looking at other areas as well. Last thing before I go into the meat and get out of who we are is Algolux is a Canadian company. We're headquartered in Montreal, and we have offices here in Palo Alto and Munich as well. But primarily all of our development is in Montreal, and we're about, including contractors, roughly in the order of about 70 people worldwide today. So probably everyone's pretty familiar hearing a lot of excitement, investment, opportunity around mobility and urban mobility. How do we improve the social fabric by creating services that help us, that get us from point A to point B, that reduce accidents, that really build other economic engines. And the aggregate total of this multi-trillion-dollar opportunity has resulted in lots and lots of investment that is going into this space. A big piece of that being autonomous vehicles. But there has been sort of a kind of wake-up calls, and things are slowing down a little bit in terms of autonomy. And I'll touch on that in a second. But fundamentally, there is this very strong economic and social engine that these mobility models hope to achieve, and there's a lot of people that believe that and are moving in that direction. Where it gets a little interesting is if you look out this door on Middlefield, probably every 15 minutes or so, or 30 minutes, you probably see one of these Waymo vehicles going by. And if you are working anywhere in the area, you see them pretty often. And really, this is a massive investment that Google has been putting into trying to create this reality of autonomous vehicles to reduce traffic accidents, to provide better services for elderly and other people that can't drive well, and help build this mobility model. So Google has a big bet going into this space. But it's, they've been working on it for quite a long time right now, and while there is a service in Arizona, it's not ubiquitous today. There's still quite a ways to go. And most companies that are in this space have kind of dialed back expectations in terms of how long will it be before we get to full level 4, level 5 type autonomy. Similarly, like another company, Cruise, just announced their Origin pod, 6-person pod, that takes one step beyond what Waymo's doing. So there's no steering wheel or anything in this. It's purely level 5 autonomous. And that'll be pretty interesting to see how long that goes from prototype to trial. But essentially all of these autonomous vehicle companies are in prototype stage today. They're not really deployed, there's not volume, they're really in prototype stage today, and they will be for a little while. We have this car here, or this manufacturer, Tesla, that is pushing the envelope quite hard on autopilot. So highway autopilot, being able to at least sort of imply hands off, although you're not legally supposed to take your hands off by their rules, on the highway. And Elon is quite a strong promoter of what Tesla's doing and where they're going. And he's claiming that by the end of this year, they'll have fleets of autonomous, level 5 autonomous shuttles out there that are going to create a new business model for what Tesla's providing. We'll see. I wouldn't hold my breath. But it's a great vision. If he said 2025, I might believe it. At the end of the year, not a chance. But that is one of the vehicles today that gives kind of this level 2+ like capability. Similarly, there's like the Cadillac Super Cruise and the Audi A8 that has similar highway autopilot type capabilities out there, and more companies are going to roll that part out. And then you've got like a Honda Accord, your normal, well-selling Honda Accord that has pretty advanced ADAS functions. So ADAS being advanced driver assist systems. So these are the annoying alarms or vibrations in your wheel when you're getting out of your lane, or more importantly, that do automatic emergency braking, so that if you've seen commercials from Subaru and Honda and others, that if you're not paying attention, it'll brake for you if you're coming up to a car or a pedestrian. And really, this is kind of our pragmatic reality of today, is providing technology that will significantly reduce traffic accidents and improve safety, reduce deaths, reduce injuries. And so what we're seeing, or what kind of the market is seeing, is a shifting a bit from the more traditional automakers to improving what they're doing from a level 2, level 3 ADAS function for improved safety, comfort, and reliability of the vehicles, and a longer term forecast when it comes down to autonomy. So it's almost like a bit of a wake up and a bit of a reality check for the industry. There's still a massive amount of investment going towards autonomy. It's just that the time frames are going to be quite a bit longer. But let's get back to kind of the opportunity here, even for ADAS. AV, autonomous vehicles, are cool, sexy, huge investments, but for the next 5 to 10 years, you're going to see a really massive improvement in ADAS functionality and a massive investment by the community on that. The problem is that today we have worldwide about 1.35 million people a year die from just traffic incidents. That's a massive amount. It's somewhere on the order of 20 times that of injuries worldwide. And this is a study that was just out last year, about a year ago, from the World Health Organization. And basically the traffic injuries are the leading cause of death for young adults ages 5 to children, young adults from 5 to 29. So it's the #1 cause of death in the world today. And about half of those are what are called VRUs, or vulnerable road users. Never say that too fast. Which are pedestrians, cyclists, and motorcyclists. And so a massive amount of people that are walking or biking are dying. In the US alone, there's about 40,000 traffic deaths a year. That's just in the US alone, and for just pedestrians, 1 pedestrian every 88 minutes is killed in the US alone. So very, very big problem here. If we can apply technology, this ADAS technology, to significantly reduce that is a massive social and human impact. And it's not just about, well, it is, yes, about saving people's lives and reducing injuries and so on, but there's also an economic aspect to it as well. Oh, sorry. And oh, by the way, 75% of these pedestrian fatalities occur in the dark. So as you know, driving in the dark or in bad weather, sometimes hard to see a pedestrian, and that's the reason why most of them are getting hit then. My personal true story is literally just over a year ago, my son, who was 12 at the time, was biking home from school, decided to take a different route to school, so we passed a grammar school that a lady was pulled over on the side of the road. It was raining, it was dark, and he was kind of behind her, and she didn't know what, and her lights were on, or the headlights and the taillights were on. He didn't know what she was going to do, but she wasn't moving, so instead of trying to go around to the right with no sidewalk, so there's no room, he pulled out to the left. At that point, she decided to take a left turn and ended up hitting him, knocking him off his bike. No broken bones, but his hand in a splint for a few weeks. And this was a late model car, so it should have had ADAS features in there. But long story short, there's still a way to go before these systems do well, and I'm going to touch on that in a second. But first, there's a pretty big economic burden to this as well. And with regards to the cost per country, this is a map per country that the Lancet, which is a health trade magazine or a health magazine, press built out. And this is basically the economic burden that each country is carrying based on these color codes. So you're talking massive, massive trillions amount of dollars that is an economic burden for traffic injuries and fatalities. But this is kind of interesting. So back in October, the AAA released a study that they did. So there's, I'll call it standards organizations out there, NHTSA in the US, National Highway Safety and Traffic Association, Transportation Association, and then there's what's called NCAP, which is, there's Euro NCAP and also North America NCAP, which basically establishes safety tests for vehicles. And very recently they started upping the level and creating these dummy targets for cars to test their systems against. And so AAA took four 2019 models, Chevy Malibu, Honda Accord, that's the one I just showed you, Tesla Model 3, showed you that as well, and a Toyota Camry, and did a number of different tests in lighted daytime conditions like this, and in darkness. And so and I'll let this play while I'm kind of talking through this. Now, the test was specific to pedestrian automatic emergency braking. So basically using cameras or a combination of cameras and radar to detect a pedestrian and automatically stop the car. So you'll say, it is funny and not funny. But these are kind of funny, but these are not, right? These is a kid, right? So basically, what they did was a number of scenarios. One is just a single pedestrian walking in front of an adult-sized pedestrian walking in front. Around a corner, two pedestrians and children kind of walking, between two cars. So the results in lighted conditions, so basically 40% of the time, the vehicle actually stopped before hitting that single adult going by. So, and then mitigation means, did the brakes get applied at all prior to hitting the target? And at least for the single adult case, in 35% of the cases, they mitigated this 20 mile per hour speed by 4.4 miles per hour. So it only hit the person at about 15.5 miles an hour. Now when they did it at 30 miles an hour, it never stopped. It always hit the vehicle. There was only one case where it did mitigate a little bit with the adult, but with for some reason, two pedestrians confused the system. Child got a little bit of mitigation at 20 miles an hour, but then that Tesla where you saw it going around the curve hit the pedestrian all the time. In addition, when they replayed these during darker conditions, evening conditions, the systems never braked, never saw the target, never saw the pedestrian. So this is kind of the latest, greatest systems. Well, okay, yeah, some say, well, Mercedes or BMW's not on there, Audi, they're probably better. But pretty much across the board, these systems don't work at all in the night and work poorly during the daytime. So keep your eyes on the road, hands on the wheel, and make sure that you brake. But
how much, if I may ask?
Yeah, please, yeah.
I mean, how much time the car has? I mean, how many seconds or how many milliseconds?
Yeah, no, that's great. So basically they put it in front, I think it was somewhere to 4 seconds or so.
Okay.
It depending on 20 and 30. The report has the specific distance that they had, but basically,
is this a vision failure or a radar failure?
these are like, for example, these cars had quite a bit of time to see the target. Like for example, it should have seen it at the side of the road. So it wasn't like that person was hiding behind a wall or anything, right? This obviously is a shorter case because you're coming around a curve. But that one, I mean, the car saw as long as the car was driving, had those two pedestrians in its sights. But to your point, Gail, this was a combination of camera-based systems, and in some cases, camera plus radar fusion.
Because like the Honda Accord is radar, right?
Yeah, exactly.
But it doesn't see it because they're not moving, or?
Well, it should. It wouldn't matter, right? It's not a differential. It should be able to bounce off that target. So with the radar.
Is there additional data, like was there any audible alarm or anything, or that's for the outside the scope?
Yes, so they did have some warning,
Okay.
but the test here was for the AEB piece of it. So if you were not paying attention, which happens often, somewhere, but when you're
Okay.
doing that, right? Oh yeah, that's right. If you're, I don't know if you've ever seen anyone on the highway look at their phone, but basically, that is really what this is meant to do, right? Also, another interesting stat from the WHO report is that about 94% of traffic accidents are due to human error. So it's primarily a human error problem. So it's not just a challenge for ADAS systems, but even AVs with LiDAR and radar and a whole bunch of cameras still have challenges here, especially under harsh conditions. So the daytime conditions alone, you would expect it to be pretty good, but in dark nighttime conditions, in snow and fog and rain, it goes from not so good to absolutely atrocious in terms of the robustness of these systems here today. So I'm going to kind of share our approach of trying to get to robust perception. And for those that have been doing some work in computer vision already, it really is kind of reimagining this perception pipeline to address this challenge of low accuracy under harsh conditions. So I'm going to dive in a little bit into camera and kind of computer vision approaches. Feel free to ask me questions. But a typical computer vision system is a mix of the camera, which has, of course, a lens, a CMOS sensor in it, and then an ISP, an image signal processor, which takes your raw sensor data and has multiple processing pipeline stages that then produce a pleasing image to your eye. And the ISP, they've been around for as long as digital imagery has been around, and they are built and optimized and tuned, the parameters are tuned, for human viewing. And then that output then gets fed into some sort of computer vision model. It could be a traditional handcrafted computer vision model, but today most vision models are created using deep learning. And in most cases, supervised learning. So you feed it a bunch of training data, and it learns how to recognize a person or a cat or whatever it might be. And then that then outputs metadata, which are in this case a 2D detection. So here are cars, here's pedestrians, but missed those. So in harsh conditions, this is a low light, glary kind of scene here. The detection accuracy is pretty poor. So basically the takeaway, the limitations are the processing that's being done off of the sort of ground truth sensor data is taking data out, denoising, deblurring, things of that nature. You're removing data to optimize for a human eye, but not for the computer algorithm. Also, there's two separate, I'll call it, tuning or optimization approaches that are going on. One is that you've got an imaging team who know all the ins and outs of the camera. So they know how to squeeze the best image quality out of that for a person. And then you have another team that really knows their neural network architectures, they know how to train things and do fine tuning and so on. And they kind of work in two different worlds. They don't really interact. And this is still the case in OEMs, tier ones, startups, etc. And then the other hard part is that for training that computer vision model, you need a lot of training data. And an easy place, for example, to get automotive data is from public data sets, whether it's a COCO data set or one of the kind of public data sets out there. And they tend to be really nice day, good image type of images that are annotated. So the person has a box drawn around it, labeled person. This one is a car, labeled car. And most of that data is good data. The problem with that is that detector, that computer vision algorithm, is biased towards good data. So it doesn't really know what good image data. So it doesn't really know what to do when it's dark out or snowy or foggy. And you could go out and capture that data, annotate it for the training, but it is way harder to schedule fog than a sunny day. Rain, maybe. Snow, a little harder, you have to go there. So it's just very difficult to capture that breadth of data, and then annotating it by human annotators that need to draw boxes around that usually is about a 10x effort. So
So
yeah,
quick question on
yeah.
that. So, I mean, yeah, the data set would have good pictures in there.
Yep.
But how much would the data augmentation aspect, help by, kind of blurring the image or darkening it, or how much would that?
Yeah, that's a great question. So definitely data augmentation supports that, but there are certain sensor noise profiles and things like that when you get into a low light scenario that get transferred and then processed through the ISP that come out in a certain different way. So unless you have a representative enough distribution across these different use cases, it's kind of hard to just through that kind of data augmentation create a well-distributed data set.
Probably if we don't do all the bad image changes to the actual business, that's what you're saying.
Yeah, it's just to do it today by either capturing and annotating or through augmentation, et cetera, it takes a lot of work, right? And it's expensive and time costing.
Most AI engines now, they work or being trained on pleasing visual data.
Yeah.
That's,
No, we're used to
pictures
that,
on the
exactly.
phone, people like to look at that.
Yeah.
And obviously, for many reasons, that's not necessarily the most optimal type of imagery for a neural network for automotive, for example.
Correct.
Are there then data sets which are skewed more to optimizing performance or machine vision versus the available data sets for human vision?
Yeah, so certainly large OEMs and tier ones go out and do capture that data. The thing is, and there are public data sets that have some, bad weather data sets, low light data sets, things like
No,
that.
I'm not necessarily the scene itself, the weather,
Yeah.
darkness, but the way that the ISP interprets the data for machine vision versus how an
Great,
ISP
great,
would
great,
interpret for
No, great question. So, so if you go through a camera tuning process, basically, and we have actually another technology, another product that automates and optimizes this whole process itself as well. You start typically in an imaging lab. You do some characterization, basically calibration of the lens and sensor, so you understand noise model, black levels, crosstalk, things like that, NTS of the lens, and so on. So you understand that. And then basically the ISP of that camera has hundreds or thousands of parameters that you can tweak to then play with what's the noise processing like, what's your tone mapping, what's color accuracy, and basically it's a manual process by that team in the lab with lab charts that they're kind of calibrating against to get something good. And then you take that camera and then you take it in real world tests and you say put it in a car or take your phone and you drive around and you capture images, and then it's like, oh, there's something really weird going with blue sky with a really green field there. It's really noisy at the edge, so how do I fix that? Go back to the lab, you fix that. You kind of do this iterative process. And generally it's a many, many months long process to get to something that the engineering team says is good. Then you invite your customer's VP of whatever into the car and says, oh, that's ugly, make it better. And then you say, okay, well, please give me the KPIs of what better means. I don't know, that's just ugly, make it better. So you go through this loop and it just takes forever. Because it's very subjective, right? And the joke
for
is
machine vision,
it shouldn't at all. So the problem is totally, and so it's super subjective for the human viewing, but the tuning process for these ISPs doesn't change for computer vision. It's people looking at an image and thinking, oh, well, if I increase contrast and sharpening, I'm going to get better computer vision results. And maybe you will, but really what happens is that your ISP needs to be tuned to get as close to matching whatever your data set is representing, because that's what that vision algorithm or model was optimized for. And generally the camera's ISP is not really producing images that algorithm likes the best. And so there's a whole other thing I can talk about that we do that actually applies an optimization methodology to search that parameter space and then find the optimal parameter set to maximize your CV metrics, which is totally objective, right? So, but you hit it right on the head. Today's process, you can't tune with today's methodologies, whether human looking at it to get best computer vision results. And what we found in that other technology is that every network has its personality. Oh, I thought everyone would like sharpness. This one likes sharpening, this one likes a little more blurry. You know, oh, everything should be high contrast. Well, this one likes high contrast, this one likes less contrast. And so there's no rule of thumb, always do this sort of an output and you'll get best computer vision results. Hopefully not too long of an answer. Yep.
You know, you said these are on prototype, you know, and in all these meetings, you know, I mean, there's so many variables in there. There's also, you know, the cloud and edge computing, the memory, the storage, big data, machine learning. You have all the, you know, internet protocols and standards and everything like that in different countries, and then the 5G. So you have all these, so many variables. There could be hundreds of them, you know, if you really get down to it. And so are they all pretty much in the prototype, basically, the whole situation? Because there's a lot going back to everything. I mean, you know what I'm saying? Even in this thing, you know, even going up a road in a mountain, you know, the windy roads, even that could be more complicated. But all the high technology, there's so many, you could go to all these meetings and there's so many buzzwords and so many traditional words that have been around for a long time. Even the IC semiconductors, you know what I'm saying? All that stuff, you know what I'm saying? Memory. And so how are they, the whole area still in the prototype, would you say, Dave?
I mean, going back to ADAS systems in cars, they've been in cars for 10 years that will do lane departure warning and so on. So automotive tends to have a very rigorous design through certification through deployment process. So the industry doesn't consider them prototypes, but are they doing the best that they could do? No.
Well, yeah, these right here, but everything else, you know, all those other variables, like, you know, the cloud computing, edge computing, all that stuff I mentioned, there's a million high-tech, even the semiconductor, all that stuff, because they all have to work together, you know, basically, right, for Internet of Things and all that. And so, is that still in the prototype stage? Even, not even just the cars as an IoT, but there's all sorts of other IoT and edge stuff, and there's so many variables. Is the whole process in a prototype stage still?
I wouldn't call it prototyping. I'd say autonomous vehicles are in the prototype stage. But I think that all these technologies are at different levels of maturity depending on the application you're going
That's
after.
right.
So in some cases they've been around for ages. You know, Internet Protocol has been around for a little while.
Yeah.
But yeah, go ahead.
Yeah. So what you mentioned a little bit earlier was when you're trying to optimize these parameters, depending on the network, it may require different optimization. So is it because these models are trained on different data sets, or they are coming from a different vendors, which it's a black box for you? So
so no, for us, I mean, we provide I'll touch on that in a second, the actual role detection stack. But we actually engage with our customers in a more open fashion. I'll call it grayish box. So because this is a collaboration to get to the best possible results, and if you're a provider that says, here's my black box, stick it in your car and be happy with it, you know, that's not necessarily always the best. But to your point, this space is constantly evolving, and we feel pretty confident where we are today, but that's the one exciting part about it. Everyone's pushing the envelope on trying to do better and better. So I talked about the robustness and accuracy piece and some of the reasons why. There's also a scalability problem, which I briefly kind of connected to. Ultimately, you need to create an architecture that is best suited for the task you're going after. Today, in many development and research environments, you're using kind of the latest ResNet or YOLO model that some university has created, and then saying, oh, I can just fit that to my application. The practical reality is you have to look at your system requirements and then build out the right model that meets your system requirements. And that's challenging. So today's off-the-shelf kind of stuff is not quite adequate. The other piece is that each ODD or operating design domain that you're using a system in has its own unique characteristics. There's the environment, there's semantics involved with that particular ODD, et cetera, that's pretty unique. And then in this particular case, annotation is one of the biggest pains in the neck. To the earlier point of how do you tune your camera for good computer vision results? Well, the best way is take your tuned camera and capture all of your training data with that exact camera you're going to go to production with, and annotate that all in training. So that's probably the best you could do today. But that means, well, for this car, I'm using the lower end sensor. For the mid-range car, I'm using that one, and for the high-end car, I'm using this sensor. And then I have different field of view lenses for different things. So my matrix of all the different camera configurations I have is probably 3 by 4. So 12 times I have to go out and capture 500,000 training data images and annotate them all at maybe $1 million a piece, or over 9 months for each configuration. It's not really scalable. So that is a massive, massive problem. So anyway, what I wanted to share is just like thinking about the problem differently. It can apply to how we're doing it, but it's also applied to whatever you're doing as well. In our case, we do something different. We totally bypass the ISP. So we're not actually producing or using an image in the traditional sense for our computer visions. We are using an image in the sense we're taking the raw sensor data, so the unprocessed sensor data, directly into our network. And what we've done is first we do that calibration process, so we understand the profile of that particular lens and sensor for this particular camera configuration. And that's the image formation model that has all the characteristics that I mentioned. We take that and use those as priors in our network, and then we actually train end to end. And so you can almost look at the early layers as a differentiable ISP that is getting, through backpropagation, information about the vision task, which are the upper layers, say object detection, that then informs the early layers. You need to process the input image, the input raw, in a way that is optimized for whatever your detection task might be. And since we also know the image formation model, we know how to respond to the noise profile of the sensor, things of that nature, the field of view of the lens. So that's one piece of it. So we have the camera characteristics, we have a unique architecture that's end-to-end and is trained end-to-end. But the other thing we do is, because we know that image formation model, we take our baseline training data set, and then we simulate that data set or transform that data set as if it was captured by that actual camera configuration. So while it's not like 100% one-to-one comparison of the characteristics, it's a really close approximation to that actual camera configuration. So it is within a few percent of as if we took that camera and captured all that training data with that camera configuration. And then what we do is we synthesize more data. We kind of, to your point, we then augment the data through synthetic data by going up and down the noise profile, through contrast, through illumination, and we build out a much bigger data set that covers all of the potential, I'll call it, parameters of that lens and sensor combination there. And since we can do that, if someone says, well, now I've got a new sensor or maybe a different lens field of view, we can then just transform our data set again and basically learn through a new model training for that new camera. So it allows us to be super nimble and support any camera configuration without having to really capture any new data. In reality, we captured some additional training data for some edge cases and things like that, but it's a very, very small fraction of the effort required. In weeks we get this done, as opposed to 9 months of capture and retraining. Does that make sense? I went through a lot in a short time, so just want to make sure that makes sense. Yeah.
So the image formation model,
Yep.
the earlier layers of the network. So isn't it like the same? Like you have a bigger network and you're feeding in an image. So what is kind of a distinctive thing about the earlier or the image formation layers?
So basically what we do here is, because these early layers understand how the lens and sensor behaves across all operating conditions, it allows us to transfer some of that learning through backpropagation to say, for detecting this sets of object classes, you may see noise like this, or you may see kind of aberrations like this, or distortions like this, and allows us to essentially compensate for that much better than a traditional image processing
So
approach.
yeah, so essentially what we are trying to do, you're saying is you get images captured and without doing any image processing, rather add a few layers to the network
Correct.
itself and let it do the job.
Exactly, yeah. And so, now you might say, of course, now you've got a bigger network, and so you need more compute, and is that going to be cost effective? The interesting thing is because we take the ISP out, today's networks already have to deal with that compressed RGB image that is coming in. So there's kind of this trade-off. We do increase the network size by a little bit, a few percentage or whatever, but not a whole lot. And but the benefit that you get back is massively improved perception. So I'm going to give a couple examples of like harsh conditions where our detector, in this case in dark night, the good thing about being headquartered in Montreal, we have access to good darkness and snow and bad weather. Right now especially, I'll just kind of run all these at the same time. So snow, and I don't know if you can see it, sort of driving snow coming through here. Really awful, noisy, foggy scenario here, and the windshield's really dirty. And then I'll talk about that greenish picture in a second. But these three here are all RGB type cameras and about a 40-degree field of view lens. So there's a lot of occluded objects in these scenarios. There's lots of objects. There's a lot of challenge in kind of making out what these are. Even as a driver, you'd be hard-pressed to see that. And then for folks that are working in computer vision, what we're showing here is what's called frame-by-frame detection. So there's something called tracking, which actually will identify objects and then with unique IDs and be able to track them across multiple frames. And that provides even better accuracy. But we love showing frame by frame because it's the baseline, it's the hardest comparison that you can do. That's not what I wanted to get. Let's start this guy too. So that one's set. And so this one here is actually, these are Sony sensors, RGB sensors. This is an on-semi AR231, and that has a 120-degree field of view lens on it, and it has what's called an RCCB color filter array. So RGB is red, green, actually red, green, green, blue. RCCB is red, clear, blue pixels. So that creates a different color profile, which is typically more often used in machine vision applications. So we were able to use our kind of transfer learning-like approach to support that camera without having to capture any new data, and just even to a whole different color filter array, much wider field of view, and so on. So we have a lot of generalization across any type of camera configuration. So I just wanted to kind of bring that up.
Question.
Yeah, sure.
True, actually.
Yeah.
So when you say you take in the raw data,
Yep.
at what layer you capture that data? Is it like true electrical signal that comes from the sensor, or you pre-process it?
Well, it's typically the companded HDR signal that comes out. So it is a debayered image. So that's usually done on the front end by that sensor. Not debayered, so Bayer data. Sorry, I said debayered. That's the first stage in the ISP. So it is Bayer data coming out of the, if it's RGB, coming out of that sensor. So it really is the first pixels of image data. And you might see some raw image. There's no real color information there per se. There's metadata for that. And then that's what the ISP processes off of.
Right, and then I have the second question. What's the latency associated with the processing?
So typically what we're running, and this is kind of a laptop type system that will demo, I'll share that information, 7,500 hertz, somewhere along those lines in terms of frame rate. So we're doing, typically automotive is 30 frames per second, some are pushing 60, but in that kind of ballpark. So that's typically the frame rate we're running at for a full detection.
What's the latency though, processing?
I don't have specific latency information. So so basically, I mean, latency would be interframe latency, right? So that would be like 30 microseconds. per second or something like that to go per frame.
Now, an additional function of the ISP is to deal with dead or dying pixels.
Yes.
If you taught the model on all the
No, sorry,
perfect pixels from training,
Yeah.
and then how will that model be obfuscated or
Yeah.
thrown out by the dying pixels?
Very, very good point. So part of
I
that.
only make a point.
Not always good ones. All questions are good. All the answers can be done.
I can attest to.
Yeah. So as part of that synthesis process of where we really expand out that data set, we do some really interesting other data augmentation work to help cover those cases as well.
Dave, what was it, 75 hertz? Is that the-
Yeah, and that would be like an NVIDIA type processor. When you squeeze it down to an application edge processor, it's going to be lower depending on the optimization, but we kind of we can lower a little bit of the accuracy for higher performance. So it really comes down to the system requirements. So surveillance type applications as well. Under pretty low light conditions, this is probably 1-ish, 2-ish lux levels here. That was indoor. This is an outdoor scenario, even lower. Really awful noise profile here coming out from that sensor. So this is super low light, but essentially doing detections under really, really harsh conditions like this. And working with a small semiconductor company and doing some of the stuff in surveillance. So just in terms of just numbers, we have been asked to evaluate our network versus public data sets as well as commercial ones that I shared. And this was against a data set of all harsh cases, so low light, snow, rain, fog, glare, etc. About 17 different scenarios. And we benchmarked against equivalently trained state-of-the-art public networks like a YOLO V3, Resident 50, MobileNet as well. And we were on the order of 2 to 3 AP, average precision, points higher than those networks, equivalently trained networks. Just for comparison, when we did equivalent sort of evaluations against things like Mobileye, Tesla, NVIDIA Drive, to any NVIDIA folks out there, they kind of came in about here, somewhere between the red and the green in terms of the harsh cases. So still equivalently 2 to 3x better than the commercial networks. And even in good conditions against public data sets, so we retrained against the public data set, so we left some room on the table because we couldn't use our raw processing per se directly. We still came ahead 5, 10, 15 AP points above them as well. So still a very impressive improvement even under good imaging conditions. So it's really robustness under all conditions. We're also doing some pretty interesting stuff beyond just camera-based. We're working with some big partners to really look at next-gen approaches for sensor fusion, working with other camera modalities, and really doing some kind of far-out interesting stuff about being able to image around corners. So this is a little bit more on the computational imaging standpoint, but it directly applies to computer vision techniques as well. This is more of just a little hint. You can see some of the stuff on our website and our research page. So anyway, that's kind of full on the technology, which was one of the things I was asked to talk about. The other piece is sort of like, how do you go from concept to getting on the road? And in full disclosure, we are in that journey. Automotive is a multi-year process to go from engagement to SOPs, start of production for vehicles. But I wanted to kind of share a little bit of kind of learning and at least kind of what we've seen. And what we're finding is traditional automotive is still traditional. There's still these multi-year development cycles. They're still following traditional processes. And frankly speaking, they should. It's a safety critical application. Going through that process provides a lot of checks and balances along the way to make sure You're not introducing unintended consequences and bugs into the system that's supposed to save people's lives and not kill them. That being said, there are a few out there that are pushing the envelope, like our friend Elon, who's basically trying out new features on the road with drivers. And sometimes that works.
That's one way to get a data set.
It is a great, and, all right, you gotta address it. I mean, they are in the catbird seat right now for data collection. I mean, it's just really amazing what they're doing there. That being said, China is really driving a much more aggressive approach to turnaround time on vehicle development. We're basically hearing about 18 to 24 month turnaround on major feature updates within China automotive. So that's actually interesting. It'll be interesting to see how that drives additional nimbleness out of the larger traditional automotive companies. And then AV's already mentioned, it's still really, they're just prototyping. They've got racks of compute in the back, and they're tweaking algorithms, they're taking things out for test drives and so on. It's going to take a little while there, and expectations have been dialed back accordingly. The interesting thing on the AMR front for these robots that are to pallets around warehouses or trying to autonomously take your luggage cart when you land on your airplane to the arrivals gate. It's definitely faster cycles. They still have some safety critical requirements. They still don't want to run into a person or into a plane or a big shelving rack. But that allows them to actually cycle quite a bit quicker. And no disrespect to any of the companies out there, but it's kind of like today they're kind of really smart Roombas, so they sort of use a LiDAR or maybe a little bit of radar to just kind of follow a little path and then figure it out. And what we found is that maybe in our engagements a couple of years ago or 18 months ago or so, they were kind of happy with where they were, but more recently they say, well, we need some more semantic knowledge of what's going on, and not just by kind of localization and kind of LiDAR. We actually need to know, okay, well, is that thing moving a person, or what is that sign, and get more semantic information to make their operation more safe and robust. And then, totally different space, but the whole video security space is one that's just exploding. There's just a very strong growth of deployments of cameras. China's #1 in terms of camera growth today, followed by the UK, actually. US is actually deploying quite a bit too, but even comparatively, China and UK are quite a bit larger than that. But the hundreds of millions of cameras that are expected to deploy, and 30 some odd % CAGR growth, is creating this very interesting space. A lot faster development cycles on the China front, 9 to 12 month turnaround on new feature deployments. And then, but the other thing, it's a very fragmented space. There's so many providers out there. And there's so many different tasks that they're doing. The ones we hear a lot about is, of course, facial recognition and security, privacy concerns around that. But they're doing many things for smart city applications, for various security and safety applications. So lots of different models, lots of different tasks that are being developed there. And in general, across these markets, I'm not going to talk about medical or AV, AR, VR, or drones and so on. They're also using AV applications. We're just deciding not to play in them. As a startup, we're trying to focus. What we find is that there's a massive amount of investment in this space in terms of building these capabilities. But probably over the last 18 months, we've seen, hey, we've got a team of 100, we've got this covered, thanks for calling, to let's talk. So there's this problem for robustness is one that just is not being solved very well by the approaches that we're seeing out there. So it's exciting for us, but until we actually get into some vehicles, keep your eye on the road, keep your hands on the wheel, and don't stop paying attention. Now, specifically talking to kind of the automotive space, I don't know, how many of you out there are actually looking at automotive as a target market? So a few of you, okay. Again, if we talk traditional automotive, they have their process, and generally it's like a number of POCs just to sort of feel you out, you know, okay, do you do what your slides say kind of thing? And then you go to maybe a demo or a deeper trial, which then is more involved from an engineering perspective, closer to their, basically their design that they're trying to target. And these early phases usually involve their R&D teams, research teams, and advanced engineering, which are a little bit closer to the production teams. And that actually can circle around for quite a while. There's even though you hope things go quickly as a startup, there's a bit of an impedance mismatch between our nimbleness and pace, which is, can we get this done in a week, to, well, it might take 2 years. And then we'll go to designing what will be in production in 3 years. But there is this kind of process where you have to work your way through with those teams until you get to basically a production target program, which could come through an RFI RFQ process or by working with this team to kind of insert yourselves into that program. But these series production programs tend to be multiple years out to volume, which kind of goes to the business model piece of, you know, there's across providers of, I'll call it software IP like we are, or even hardware IP to some degree. Usually there's some bit of NRE, non-recurring engineering cost, which is paying you to make your thing be much more suited to what they're trying to do as opposed to what you currently have. And in many cases, there's either a flat-out license that gets you the IP or a license and royalty component. And depending on that mix, the size of the volume and the timing of that volume has to come into play on how you kind of build out your model for those companies. And that's kind of been a traditional IP licensing model. What's interesting has been especially the move towards more autonomy, since those companies are sort of looking at these platforms differently than a traditional car that gets built and deployed. They're looking at these as really a living platform, and they're starting to be more interested in potentially SaaS models for the whole autonomy stack, potentially. And so, yes, many of them are still doing more traditional licensing and royalty models, but we're starting to hear more and more about, well, we're considering other models to look into. So something to keep an eye on. And then there's open source models today. You've got Apollo from Baidu, for example, which is a full autonomy stack that has been put in the open source community. And they, of course, want to sell their services and data center capabilities, but yeah.
How would the SaaS model work?
Yeah, so basically you have a subscription of some sort to the software stack that's running in a vehicle times whatever number of vehicles on a recurrent monthly basis or quarterly basis or something like that. And it allows you to be more nimble in terms of your deployments that way.
But is it based on the usage or the computation?
This is a very open topic. It really depends on what works for you as the supplier and the company as the receiver of that. So it could be based on computation, it could be based on just a unit, it could be based on miles driven. Really, there's open variables on how it makes sense for either company. A lot of the, there's interesting companies out there like Voyage, it's based locally here. Their autonomy use model is retirement communities, right? They're not going to be a cruise that's driving around San Francisco. They're going to be in these big Florida and Texas retirement communities and creating a shuttle service there. So they may have a different economic view on how they want to deploy versus, say, a Lyft or an Uber or Waymo or whoever. So hopefully that helps.
Excuse me.
Yeah.
So, in the context of an autonomy stack, how is government certification going to be compatible with that if it's continuously evolving? for which you charge as part of the subscription.
So-
Where does government certification come in to allow continuous release software?
I think the government's trying to catch up on how to do this, how to handle this. Right now, they have policies in place of letting safety driver-enabled autonomous vehicle testing to occur, and they've also recently been giving out some licenses, if you will, for not driverless operation. But there's one thing is that road policy is in the US driven by the state. There can be some federal mandate to that, but states have their own control over that process, which causes some challenge, right? If you have a, say, a trucking application, autonomous truck, that's driving freight across state lines, and how do you know that it's going to comply with all the different state rules on autonomous driving, right, which is still being evolved. So this is a whole wild west right now. There's just a lot of unknowns, but ultimately there's going to have to be some collaboration between industry and the federal government and the state government to drive that. And there's plenty of work going on right now. I'm not saying it's not going on, but there's nothing really, to my knowledge, that's well established, defined at that level.
I guess how can you sell product to your customers when the deployment by your customer requires approval by regulatory bodies?
So in the case if we're going after an ADAS application, it's a very well established process of certification.
Okay.
So you know, there's different levels of safety, ASIL certification, things of that level, depending on the safety critical nature of the design. And so that is typically owned by the perception or the vision system or the safety system, I'll call it integrator or developer. We would be a software component in that. So for example, a Bosch creates the forward-facing camera for customer at OEM X. They need to go through that type of certification, and we would contribute into that process based on existing standards. There's other standards that are starting to emerge, like SOTIF, Safety of Intended Functionality, that are trying to bridge the gap where ASIL kind of falls off for these applications to actually a more functional view of a perception or automated system capability. And that's still evolving on how that works out. But yeah, we've got a bit of a road to go. But at least for ADAS, these systems are on the road today using neural networks and so on that have passed certification. And you can certainly look at that and say, are they adequate? And if you look at it this way, yes. If you look at it that way, maybe not. Right? So things are moving really quickly, and certification and governments don't really move that quick. So, good question. That's great.
Yes, so would you say that automotive, full automated driving is still in its very early stages?
Yeah.
0.8 Bluetooth technology, like we are at Bluetooth 5.0 right now, where we can switch between call and audio and switch to different devices seamlessly. But right
I don't
now,
think we're even there. Nothing seamless about it.
no, in the sense that it's pretty early, or the chips or the software itself is not so evolved yet. The models or the architecture is not so evolved yet, where they don't know what to make together and then make it more efficient. Like Algolux found something to bypass entirely in a way that.
Yeah, one of the limitations, which is how can we make these systems more accurate under all conditions, so
Right.
that fundamentally it enables much better safety and reduces the opportunity or the chance of accidents and injury, and allows scalability, so there's an economic benefit to being able to apply it to the right technology from a camera or sensor perspective. And so we saw those as some fundamental challenges. There's plenty of other challenges out there in this whole stack, but for us, this area of really improving the perception piece of it, helping the vehicle or the machine see better, so to speak, is something that we had kind of a unique set of knowledge from machine learning and computer vision and computational photography that we kind of pushed together, and we're able to solve that problem. If you went and said, solve the electrification problem, that's not us, right?
One quick question. So, as you said, you train the deep learning model, neural network, with the input that should have gone to the ISP, actually goes to your network.
Correct.
So, when you go for actually predicting or actually labeling or detection,
Yeah.
you need to have the same input coming in right to the network.
So for
Or-
us, yeah, we don't. So we do capture our data set of training is essentially raw data that is annotated. So we do some ISP post-processing for a human to be able to see the objects they're annotating, but that data set is primarily raw data that we have. We augment that with some captured JPEG type data as well, so it's not 100%. And that allows us to easily transfer that to other camera configurations. Did that answer the question?
Yeah, kind of. So, I mean, even if you are given a normal post-processed image from the ISP, it should work properly. The network, the initial boot. I mean, how does that?
So we have used post-ISP process data to go into our detector layer. So basically, we bypass our early layers. We get much worse results. We do get better than if we see someone. We have compared actually just our detector versus other detectors, and kind of our detector is still outperforming the ones we've benchmarked against. But basically, by having that full end-to-end approach, gives the dramatic improvement in the detection performance.
But what is the practicality of having that thing inside a car, that network functioning in a car, wherein the cameras or the car manufacturer will be having their own hardware specs for the cameras
and so that's how we're working with those manufacturers, because basically you can look at it as we're creating a slightly bigger network to run where their detector only is running, and then we're just bypassing that ISP and just going there. So that's basically kind of the trade-off. So if you can handle a little bit bigger network but get twice the detection performance, kind of a good trade-off.
Thanks.
So, as a company, you guys work with existing Waymos, have customers, what are you messaging with them?
Yeah, so we had a Series A funding almost 2 years ago now. GM Ventures was the lead investor in us. Drive Capital out of Ohio, Columbus is another big investor, and then we got a few out of Canada, so we can maintain their Canadian heritage there. And we have we've been engaged with public knowledge, but many OEM and tier ones currently. And right now, those engagements are in the transition from, I'll call it trials, to actually targeted production type programs. So we're working our way through that painful long cycle, but that's just the way the community works. Now with some, they're a little faster. AV's a little more. A lot of them are ADAS, but there are a number of AV type applications and AMR type applications, so they move a little faster.
So you are targeting this industrial robot space as well?
Correct.
And do you find technologically or cost-wise that there's a factor of overkill, or is it what's your
No, actually, it's interesting.
compared to the other model?
Yeah, it's kind of interesting. So, at first glance, you would think, well, it's a warehouse robot. Like, what's a harsh imaging condition for a warehouse robot? The practical reality is that these warehouses, they want to reduce electric costs, so they try to turn the lights off as much as they can. They also aren't all built the same way. So some warehouses have windows on one side of the building that at noon, it's great. At a certain time of day with that sun glaring through the side of that building is really screwing up the robot. And so it is surprising there's a bunch of harsh conditions. And then in some cases, there's even environmental challenges where it's a cold room. And so they actually will get fog in this refrigerated room, if you will. And so it's, it's more harsh than you think. And then you have the whole mining and that whole industry, which has its own, they've been automating things for quite a while, but they have really challenging imaging conditions, if you will. So in many of these cases, a lot of them have started with a LiDAR type approach, and then that's causes challenges, like if it's foggy, your LiDAR doesn't really work very well. And then you don't really understand what's in front of you. You can detect an obstacle, there's something in front of me, but you really don't know what it might be. So it could be a big piece of paper that's fine to drive over, right? So anyway, that's that case. It's not overkill. They actually put quite a bit of compute in there in those vehicles.
What cost-wise?
Those systems tend not to be too inexpensive, and the volumes in general are not bad. They're not automotive, but you're talking, these companies are talking about tens of thousands of, vehicles and units or robots out there for application space. So it's not the 80 million a year passenger vehicles out there, but it's actually pretty reasonable. And they have a different economic view on budgeting for these capabilities than automotive manufacturing. Any other questions?
Just a quick one. For the NRE deals and projects that you work on, I'm assuming most of that is involved in the data science part of it, or are there other big chunks?
Yeah, a lot of it is tailoring the network for their particular platform. For example, I wanted to run with that particular camera, this particular hardware, this processor, things of that nature. So that.
Do they give you the data set, or are you supplying the data set?
It's all the above. It depends on the application. Typically for these, they have a very specific use cases that they want to satisfy, which we probably don't have all the data that we need. Do we have exactly that sign in Japan? Do we have exactly that, road marking in, southern Spain versus the one in the UK? So there's things that we have to augment some of the training data with, but generally we have a pretty good generalization across most operating conditions, and there's fine tuning with some regionalization.
How does your system work with a multimodal approach? Multiple cameras, radar, LiDAR, does it expand to that approach?
Yep, absolutely. Yeah.
So we get better?
Yeah, I would say, right, if you, every sensing modality has its strengths and weaknesses, and so fusion is, already today in automotive, they're doing fusion of radar and camera, they have ultrasonics in there as well. Autonomous vehicles have been very LiDAR heavy, but now you're seeing really a growth in the cameras that they're adding to that, and camera LiDAR fusion has been around for longer, with radar has been around for a long time.
Does the fusion of the data happen in the neural network?
Yeah, so I kind of did my little hint on some of the work we're doing on fusion. Basically, we have a number of different approaches. Typically what you're seeing with fusion today is what's considered late fusion. So you have the camera is detecting these objects out there, the LiDAR is detecting these things out there, and then you do kind of this minority report thing where, okay, I see the same things, and who do I trust more, depending on maybe the conditions. And that works pretty well. So we have that as one of our options. The other thing that's more interesting is we do what's called early fusion. So we basically have the camera network, which is doing the early sensor processing. We actually do the same with the LiDAR. We actually will then fuse the early sensing data, so pre-feature data, and then actually do detections off of that fused information. The interesting thing for the LiDAR case, what that allows, one of the things that we did a study on, you can see the report on our research page, or the paper on the research page, is the dealing with asymmetric failure. So in foggy conditions, the camera still kind of sees what's out there, but a LiDAR due to the backscatter, just once that fog gets thick enough, just nothing, right? And so we, through that early fusion approach, we can actually understand the degradation of both signals and then actually adjust to the sensor return, if you will, and maintain a much higher level of accuracy down that curve. Eventually, there is some degradation in our detections, but we're kind of degrading at a slower pace than a traditional late fusion approach. So hopefully that answered.
It
Any other questions? Was this helpful?
Yeah.
Very
Really
good.
interesting.
Awesome.
Thanks,
Well,
Dave.
definitely appreciate you listening, and hopefully it wasn't too boring. Yeah, do you see an opportunity where Algolux might be helpful to work together with you? Yeah, let me know. So I'll be here for a little while to chat.
Let's give it up to Dave.